Welcome guys to the second part of exact equations. This time we're going to talk about exact equations with integrating factor. These type of equations will look exactly like exact equations, so they will have the same form. So we'll have mxy plus nxy y prime equal to 0. However, the first step, if you watch the previous video, the first step we need to verify is that they are exact. So what I mean by that is we need to check that my of nxy must be equal to nxy. So the partial derivative of n with respect to y must be equal to the partial derivative of n with respect to x. They must be equal. So if they're equal, then we say that they are exact. However, there will be cases where you'll find problems where you have this form, but this case doesn't hold. So the partial derivative of m with respect to y is not equal. So we'll have this is not equal to nx. So, and then what do we do there? So the next step will be to find an integrating factor. So the next step will be to find a function mu, that this function can either depend on x or depend on y, depending on the problem. And we'll do an example for each, so we'll see how to see which case it holds. So, and once we find that equation, then we will multiply this equation by mu, the original equation. So we'll have this, and if we multiply them by mu, then if you check this again, so let's call this let's call this m tilde or n hat and n hat. So then if we check this, then they're gonna be equal. And then we can proceed with the previous method to solve exact equations. So let's do an example for this and we'll see what I mean with all this, okay? So the first example, let's jump to here. So the first example I'm gonna cover is the following. So let's put example 1. So the example 1 is given by 3xy plus y squared plus x squared plus xy y prime equal to 0. So as you can see, this has kind of the same structure. So this looks like we have a function m of x and y that is given by this, plus a function that n that depends on x and y that is given by this. This is equal to 0. So we have the form that we want, but now let's check if they are exact. So we need to check that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So let's see if we get that. So we'll get on the left hand side, we'll get 3x plus 2y is equal to 2x plus y. So as you can see here, we don't have equality. So now what do we do? So the next step, as I mentioned before, is we will have to find a function mu, and this function can either depend on x or it can depend on y depending on the problem. For this problem, it will depend on x, but I'm gonna write the two cases and we'll see when it depends on x and when it depends on y. So we can check both. So let's put here if depends on x, then we'll have that the derivative of mu with respect to x will be equal to mx should be my minus nx divided by n mu. So if the function mu depends on x, it must satisfy this equation. However, if it depends on y, or function mu should satisfy the following equation. The derivative of mu with respect to y must be equal to and x minus my divided by m, mu. Sorry, my m looks like a mu. So there. So we have these two equations. So we just need to check if either depends on x or depends on y. As I said, this problem will depend on x. So we're gonna just follow the formula for x. So what I mean, we're gonna follow this way. So we have m of y. So m of y is just 3x plus 2y. We calculate it here. And we have n of x, so that's minus 2x minus y. And we need to divide this by n. And what is n here? N is x squared plus xy. And this must be equal to the derivative of mu with respect to x, multiplied by mu here. Okay, so if we solve this, we get x plus y. And here we get, if we factor the x, we get x plus y mu. So we'll get this, we can cancel. We will get 1 over x mu must be equal to the derivative of u with respect to x. So then we can solve this problem to find what the value of mu is. So we'll have the following. So we'll have the mu over mu is equal to dx over x. And this will give us, if we integrate on both sides, we'll get ln of mu, sorry. And on the right hand side, ln of x. I'm not gonna care about the constant here, so I'm just gonna leave it like that so we can get rid of the natural logs. And we can say that mu is equal to x. So we have found our function mu. So now the next step will be to multiply this mu by my original equation. So this was my original equation. So let me square it here. Well, not square it, just to put it in a rectangle. But let's, so now we're gonna multiply that by x. So we will have the following. We will have 3x squared y plus, so it should be 3x squared y plus xy squared plus x cubed plus x squared y prime equal to 0. So we multiply our original equation by the mu function that we just found. And now what we can do is check if this new m that I'm gonna call m hat and this new n that I'm gonna call n hat, we're gonna see if they're exact. And what I mean by that is that we're gonna check that the partial derivative of m hat with respect to y must be equal to the partial derivative of n hat with respect to x. So let's see that. So here we'll have 3x squared plus y squared. I'm sorry, not plus y squared. Should be plus 2xy. And this should be equal to the partial derivative of n hat with respect to x. This should be 3x squared plus 2xy. So now we see that we have an equality here, so we can say this is exact. And now, if we remember the previous video, if you haven't watched it, please watch it. If we find that an equation is exact, then we say that we have a function psi that depends on x and y, which is equal to c. And this will be our solution to our differential equation. Again, I'm not gonna solve this part. If you want to see how to solve this type of equation, please watch the previous video and I covered 2 examples on this. So the next example that I'm gonna cover is for the other case where the mu function depends on y and it doesn't depend on x. So for the second example, we're gonna do for this. So let's cover the second example. So example 2. So our example 2 will be the following. So we will have y dx plus 2x minus y ey dy equal to 0. Okay, so this is not our typical equation, so we have to put it in the right form. So this is mathematically wrong, but you know, this is how not most schools teach it, but some, for sake of understanding and for sake of, I don't know, the students getting used to this in a better way, they do it this way, but it's not mathematically correct. So what they do is they divide everything by dx. And then what they get is the following. Okay, so as I mentioned before, this is not mathematically correct, so but it helps for the sake of solving the problem. So we're going to stick with this notation, even though it's not mathematically correct, because you cannot divide by a differential term. But as I said, we're going to stick to this way just to solve the problem. So now we have our equation in the form that we're used to. So from here we can say that m is equal to y and n is equal to 2x minus y ey. Okay, so now if they are exact, then we should have that the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. So let's see what we get. So here on the left hand side we get 1, and on the right hand side we get 2. As we can see, these are not equal, so they're not exact. So now what we're gonna do is to see if we can find a integrating factor, a function mu, that when I multiply the original equation, it becomes exact. So, and as I said before, this example will be based on mu depending on the variable y. So for this, we'll have that the mu dy must be equal to nx minus my divided by m. So by doing that, we'll get nx is 2. Oh, here I forgot the mu. So my is 1, and m is just y, and this is mu. So we'll get the mu dy. So what we're gonna get here is 1 over y mu. So therefore we can solve here. So we have the mu over mu, and this is dy over y. So we'll have again here that mu is equal to y. Okay, so I skip a step here, so just to make sure. So this should be equal to, if we integrate on both sides, we get ln of mu equal ln of y. And plus a constant, but we don't care about the constants for now, so then we can get rid of the natural logs and we'll get this. Okay, so now we have found our function mu. We have found our function mu, so we can now multiply this function mu by our original equation. So let's do that. So we'll have y squared so y squared plus 2x minus y e to the y prime must be equal to 0. Okay, so we have this. So let me just put it in a different form. So maybe I can put it 2xy minus y squared e to the y prime equal to 0. Okay, so now we have transformed the original equation into this new equation, what I'm gonna call this m hat, and this part here I'm gonna call n hat. So now we need to verify that they're exact, that this equation is exact. So to do that, we need that m hat, the partial derivative with respect to y, is equal to the partial derivative of n with respect to x must be equal. So let's see, what is the partial derivative of m hat with respect to y? We get 2y here. And what is the partial derivative of n hat with respect to x? So we'll get 2y. As you can see, now we have an equality. So now we can conclude that this equation is exact, and therefore we can find a function psi that depends on x and y, which is equal to a constant, and this function psi will be the solution of our differential equation. Again, if you don't know what I mean by this, go back to my previous video and you will see 2 examples on how to find this function psi. Again, these type of equations are when they look exact, but when you verify, they're not exact. So then we need to find an integrating factor that we can use to make the equation exact. And the important part that I want to mention here is this mu function can depend either on x or can depend either on y. And we have 2 different formulas for that. You can write them both and see which one works for you. It can work like either work for y or either work for x, but it won't work both at the same time. So just make sure that you verify for both, and then that you can get a solution. Okay, again, thank you for watching. I hope this video made sense and that this clarified some questions that you had regarding these problems. Again, please leave a comment if you have any question. Please like this video.